Yes, it's nice to be back in France. I go here quite often because I have family in France, and as he alluded to, I spent a year in Grenoble, but it's a long time ago, more than 20 years. So I have some feelings for this place. So I was very positive when I got this invitation. Now, if you look at this title, it looks like I'm going to give a very, very technical talk on a very, very technical little detail, and it should go into one of the sessions. But I think I'm going to try to avoid that. And I'm trying to show you that there are some big issues here, and that those are the ones I want to discuss. So in a sense, the setting here is the following. So you're facing some optimization problem, and you realize there is stochastics in it. Of course, some of us realize that all the time, and some of us don't, but I think it's always there. But you're facing it. But the problem I'm kind of attacking today is, but there are so many of them. So I have random variables, but I have so many, and they are dependent. And I think that the dependency is important for my problem. So cheating with dependence is going to be breaking down my problem. So I have extremely high dimensions, and now I'm talking about dimensions of the random variable. Of course, the optimization problem is big too, but that's not really the issue. And I'm going to carry you up to problems with about 25,000 dependent random variables. And I'm going to, well, they are dependent, but I'm going to resort to only correlated. I wish I could go further, and that's things we're working with, but so those are the things. And so what do we do? Now, I'm going to do it in the context of vehicle routing and with stochastic travel times, because I'm a bit fascinated with it, and because it's something that when I go to vehicle routing conferences, I feel people don't have a grip on at all. And I have to say, I can still proudly say that I've never published on vehicle routing, because this is not published. Still fighting with referees. I always do. So that's the setting, right? So even though I will be talking about that specific problem, and I will carry through with it, you will see that there are some sort of more general issues that show up, and that's why I put this in a plenary and not in a technical talk. So again, we have this basic logistics problem. Of course, I say thousands, or probably tens of thousands of papers on vehicle routing, and of course lots of applications. So what do we have? We have a set of customers with demands. We have a set of vehicles with capacities. We have travel times between customers. We have time windows, right? We have service times. And of course, we have all sorts of variants, and you know all about that. So, and I'm partly interested because it's useful in city logistics, so let's again see where it shows up. Why am I interested in city logistics and in context? Well, stochastic travel times are probably more important in the cities than in the countryside, right? So it's that kind of distribution that shows up. And much of the work we're doing in this work is actually taking place in China. So the example I'm going to give you today is from Beijing, but just now we're working very hard to get proper data for this in Chengdu. And so it's a city of 15 million people, and we have quite good speed data from all the taxis over a long period of time. So we're working with that. But for the moment, I'm just doing this generally. So again, a major tool for planning distribution, right? Could be from major warehouses to shops, it could be from depots to warehouses or customers, it could be the last mile. So which truck, bicycle takes care of which customers, and what routes should trucks, bicycles follow. And you know that, so that's why I talk very fast on that part. Now, I would say, obviously, but you don't have to agree, so when you plan a distribution like this, so now we're going to distribute in a city with a number of vehicles, delivering to a number of customers, and of course we are worried about stochastics as time goes by here, so there are always things you don't know. Now what you don't know depends on the context, it depends on whether you're planning just before you're leaving the depot, or this is a general plan made for the next week. So of course what is uncertain depends on the context. But what are I think the obvious ones is of course speed, travel times. Now the literature usually talks about travel times, but when I do discretize in time and space, then to me speed, travel times become a bit awkward, because if travel time changes as you go along, well, the travel time is the travel time, it doesn't change as you go along. So, but speed changes, so I think I like better to use speeds, but of course it's the same thing. But most of the literature here would talk about travel time and not about speed. Demand, of course, that's where there's most literature on stochastics, service times, and of course sometimes you don't even know the customers. So that could be stochastic too. There is coming a bit of literature on the last one also, that's probably the hardest. There is some literature coming out now. There's maybe more, but this is one I know. So there is, mostly it's on stochastic demand, and it's a very simplified setting, most of it. You're planning a route, and let's say you're picking up, just to take an example, and you pick up until you're full, and then you go back to the depot, and you empty the car, and you pick up where you left the route, and you finish the route. And you have an assumption that you only go back once. So sometimes that's the right problem. If it's the right problem, it's fine, but it's kind of simplified, right? So that's where there's most literature. And you see a few reviews there. So what about the random variables? Well, as I say, people have started to look at randomness, but almost exclusively independent or uncorrelated, sometimes a bit unclear, sometimes even who cares dependency. By that I mean, sometimes it seems that when you read literature and people don't talk about correlations or dependence at all, they behave as if they had let them be independent. But actually achieving independence or uncorrelated, which is a bit weaker, is also an issue. So it's not like these papers are about the independent case, they're about I don't care case. You know, after you've solved your problem, you have actually used the discretization, a distribution, and it has a certain correlation. But when you read the papers, you have this feeling that that's not really much of a concern, whatever I ended up with. So even though I'm distinctly talking about correlated, and of course not all the correlations being zero today, but actually achieving uncorrelated random variables in a stochastic optimization problem is an issue almost as hard as achieving any other correlation. It's when you have the I don't care correlation that it possibly gets a little bit simpler. So that's something to think a little bit about, if you think that the correlations, dependency are important in the first place. So, and the reason is usually, not at least, that we believe the phenomena are independent, but we don't know how to handle it. So either is this I don't care, or I don't know that I should care, or it is, yes, I know very well what the issues are, but I don't know how to do it. And that's been, I think, the situation until now, and this is an attempt to show one possible path of trying to handle that in at least some kinds of problems, a little bit more problems than the one I discussed today. So, I mean, typical examples of dependence that will show up, you're distributing beer into a city, well, the demand at the different spots is not, well, the weather is nice, they all sell a lot of beer, right? So they are clearly positively correlated, these demands. Or service times, of course, may systematically depend on the weather. If it's really terrible weather, the unloading and loading at every shop takes more time than when the weather is nice. So we can give lots of examples of correlate. The problem when things are positively correlated is, right, if you have a problem with delays because of the service time, it will just add and add and add, right? They won't cancel out, which they would if they were negatively correlated or if they were even independent. So correlations are nasty in optimization problems. And of course, I think travel times on streets in the city are random, but I think obviously more probably positively correlated, right? If there is trouble, well, there is trouble both here and there, right? Not with probability 1, of course, but if there is problem on this street, there is probably problems on the next street too. And if the probable is there, even if it's weak, well, then you have positive correlation. So we're going to, in this work, to cover the case where speeds in a city are correlated in time and space. And what do I mean by that? Well, I'm going to discretize time. Space is discretized, so that's no problem, right? But I'm going to discretize time. So speeds on the same link in neighboring time periods, they are correlated. They are fairly strongly positively correlated, right? If you think about, especially if the time periods are short, well, there's an example here. If the time periods are short, if you have a very low speed on a link in one period, it's probably very low in the next. If it's high in one period, it's also probably very high in the next, although that one is, of course, more likely to change abruptly. But positive correlation is quite kind of obvious, I think. The next one is that speeds on links, roads, that meet an intersection are correlated. So if there's trouble on one link into a section, probably, possibly even, there's trouble on some of the other links. Well, if that's true, you have positive correlation. So basically, this is what we do. So we're thinking that these should be positively correlated. And this is new. I did this work some years ago. As I said, I'm still fighting with the referees. But so there are a few papers now coming out that trying to walk down the same path as I'm doing, not in terms of methodology that I'm going to talk about, but actually getting the dependence right. But there are fair number of papers that talk about time dependence, and I'm sorry they stole the term, because all it means is that travel times, speeds, are different at different times of the day. No, that's fine use of words, but it means that this nice word dependence I cannot use for stochastics. I've tried and I failed because I'm being told it's taken. So you should be aware when you read about time dependence in the literature, it means that the speed, travel time, depends on the time of day, which of course is important, but it doesn't mean that speed from one period to the next is actually time dependent. So you have time dependence of morning, afternoon, rush hour, but you still have independent stochastic travel time, if it's stochastic, between 5 and 5:05. So you may have basically zero speed at 5, and at 5:05, you have free float. Here is my example that I'm going to use today. I don't know how many would immediately see that this is Beijing, but it is. So it's a rough map of Beijing. It has so of course it's only the main roads. It's 142 nodes, 418 links. And if it's two-way, I count it as 2 links. So that means if I split the day into 3 time periods, I will have 1,254 correlated random variables, and if I split it into 60 time periods, which is basically where my laptop gives up, so not really algorithmically, but the laptop gives up, and I have 25,000 correlated random variables. So this is kind of my example setting. And this is going to be a 2-stage model still. I want to go dynamic, but that's much more difficult. So we're trying to, we have a 2-stage model, and it basically goes like this. So in stage 1, in the first part, you pick routes, sequences of customers for K-capacitated vehicles with visiting end customers. This is just as you do is in all the deterministic ones too, right? But it just there you don't distinguish between the stages. But that is a route. It's a sequence of customers. And in the second stage, for every pair of customers that you're going to visit, you're going to pick the route between those 2 customers that has the shortest, well, I'm going to be a bit more specific, but the shortest expected travel time given traffic conditions when you start from the first customer. So the idea is, again, try to forget the math, right? So when the truck leaves the depot, it knows which customers to pick and in what order, but it doesn't know how to travel from customer to customer. If you get a bit confused, no, that's okay, because you should. And then when they leave a customer, we assume they have this little machine in their car, right? And it uses present traffic conditions, and then it calculates the shortest route in travel time to the next customer. But we don't update en route between 2 customers. I'm not saying you shouldn't, right? But we don't. So you have the game, the route is determined. And of course, we have some objective function, and the objective function in the example I'm going to give you, but I've run it with many others, is to minimize expected excess travel time. So, if you wish, overtime pay for the drivers. No gain of arriving early if they have an 8-hour working day, but the penalty if you arrive late. And now you see that the travel time is going to enter into the model. And again, just if you think about stochastics, you've not used it, if you have symmetry in a stochastic model, like a penalty for being early, a penalty for being late, probably stochastics is not very important. But it's asymmetric, right? You have a penalty for being late, but not for being early. So that is the setting for this example. Now, the map data I have are real, but for this example I'm giving you, the speed data is going to be fake. Okay? Also meaning they are reasonable, but they are not right. So we have to make sure, I have to make sure that I don't create some examples for you where my methodology looks wonderful because in fact I've set it up so that any little smart thing will look wonderful. So what does this funny sentence mean if you don't know what it is, if you haven't seen it before? It means that the expected behavior of the solution from the stochastic model is about 10% better than the expected behavior of the model from the deterministic model applied in the stochastic setting. Because even if you have a deterministic model, you still are subject to the stochastics when you drive, right? So this we call the value of the stochastic solution. That's sort of a technical term from stochastic programming. But here I have it around 10%. So that means stochastic matters, but I haven't set it up in such a way that it matters so enormously much that whatever I do will look really wonderful. A bit because I don't have real speed data. Well, actually, I have now, but I didn't have here. So now this part I'm going to now, I think is a bit of general interest and a little bit more general than just is my problem. Now if you think about the vehicle routing literature, almost all of it, we operate on the customer-to-customer network. So we have the customers in the nodes, and then we have travel times or whatever you have, distance between the nodes, and you calculate that from the underlying data. And I'm going to argue that when you do stochastic speeds, you can't do that. Well, first, a very practical reason. If you have measures like on road links like speeds, of course they are probably on the map and they have nothing to do with your customers. If they're collected with the system, toll roads, traffic management systems, of course they don't know where your customers are. So if you have that kind of measures, they would be on the road links. So that's a practical argument. But more important are the other ones. Well, you might have collected your own data, of course. You've been operating for a long time and you collected all these travel times or speed data. But dependence is going to be tough on you if you're trying to do that. One reason is that there are many pairs of customers, right, that share links. So that creates positive correlation in speeds. But not only that, but because you don't drive the same route every time, they don't share the same links all the time. Now, some of you may be very good in statistics, you can work this out. But I think when you combine that now with time periods, and it will matter not only which time period you start the trip, but when in the time period you start the trip, I think you're down a tough road. But I won't say you can't do it. But right, that would be a kind of a natural thing to do, but I have collected data, or I will start to collect that. Well, it's not quite that simple, I think. I think we would need also an enormous number of data points. I think of my 25,000 random variables, I think you would need an enormous number of data points to kind of come up with a reasonable set of data points so that it actually means something as a description of the true underlying stochastics. And of course there will be a lot of customer pair time period combination for which you have no data points at all because you've never done it. So there are all sorts of issues if you want to walk down that lane. But I think this is kind of the most important one, and this is why we decide, no, we're not going to go down that road with a customer node network. It is, right, if you there are a few papers that say, okay, yes, but let's assume that the speeds or the travel times between every pair of customers is uncorrelated or independent. Whichever, independent is worse, of course, but that implies that not two pairs of customers ever share a link. Because if they do, they would be positively correlated. So if you think about Manhattan, right, also because it's so easy to see, so you have a customer sitting in a node here. If you have more than 4 other customers, they will have to share a link out of this node, and then they would be positively correlated. So I'm not saying you couldn't do it, and you may show that in a certain context it gives reasonable results, boop, 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 right, that's numerics. But the assumption itself is kind of meaningless. It cannot be an assumption on the problem. Why do I say that? Think about demand. Well, sometimes saying that demands are independent makes a lot of sense. It's totally meaningful. In other case, no, they are dependent, but let's assume they're independent. But you know, the independent case makes sense, right? But for travel speeds, no, they don't. So there are some problems there. So we will operate on the map. Now there are some other papers that discuss this issue between the customer nodes and the map. But the issues are different, but it sort of end up with the same kind of conclusion. So there are some other works go that way, but they are not in my context, but there you are. So we have to operate on the map. I would claim that. Do we have data or not? Now, why do I ask that question? Well, we all know that when we write OR papers, especially if we have an algorithmic mind, we invent data, right? And we all consider that okay. There's a section in the paper talking about event, how you generated your cases, right? So we all accept that, and we want them to be reasonable and so on. And I will ask a little bit here, if you don't have data, or if you have data, what are the issues? And you will see they are actually quite similar. So, right, so if you have data, you could calculate correlations. There is an issue of whether or not your estimates are good, but at least you can calculate them. If you don't have data, you have to guess or model correlations, right? That's what we usually do when we do things. Now, of course, when we guess a correlation matrix, this is a technical term, right? But is it positive semi-definite? It means the matrix you guessed was your correlation matrix. Is it actually a correlation matrix, or is it just a matrix? Okay, that's what this says. If the answer to that is yes, yes, it is a correlation matrix, the one you like, I don't know, but you guessed it, you used your brain, you used your knowledge of the problem, you guessed the correlation matrix. I'm sure it's quite good. But is it really a correlation matrix? Well, there are methodologies for checking that. So maybe it's no, and then we have to fix it. And there are methodologies for fixing matrices to find correlation matrices as close as possible to the one you set up. I won't go into that, but that exists. And then eventually we can generate our scenarios if we have a correlation matrix and we have the marginal distributions. So without data, we can just assume a distribution, right? And that's what we normally do. And I just want to say that that's maybe not so easy here. So all we need is, in my case, a 25,000 dimensional dependent random variable or a correlation matrix of that, right? So I need to guess on that one if I don't have data. So we just invent one. That's what we usually do. So I'm not attacking that approach of guessing. We do it all the time, right? But how is to do it here? Well, first, I think we want one that makes sense, right? And what do I mean by makes sense? Well, it is a correlation matrix. But if you have, let's say, if you end up with two links nearby each other in the same period with a correlation of minus 0.9, you know what's going to happen to the root, right? It's going, those two, the code is going to try to put those two on the same route, because this minus 0.9 means that the travel time on that route will be very deterministic. So, and then, if you're testing an algorithm or you're doing investigation into a problem, do your results mean anything if you have been running around with correlations like that? This can happen if you have to fix your guess. It can easily happen. So we have to be careful. We want one that makes sense, right? So that when we have done our testing, we know that testing is at least applied to a problem that could have been the right problem. And that's not obvious here. And I would say it's almost impossible, and truly impossible as a general approach, to guess a dependent distribution of this type. Why is it that? Because it's basically impossible, I would say, but it can happen, that you guess a huge matrix, and you use your brain, okay, this must be 0.8, because it's the same link in two periods, and the period is only 5 minutes long, and you make very intelligent guesses, but something funny is going to happen somewhere, and you're not going to get positive semi-definite. And then it's not a correlation matrix. And you can probably, it's, for example, very difficult to sample from a matrix, from a distribution that doesn't exist, right? So it's more than a detail could be that your correlation matrix that you think is not a correlation matrix, because you don't have a distribution. With data, I haven't really done, I'm working with it now, but you should also be aware that even if you have data, you can calculate the correlation matrix if you have data on all the links. But I think there's a big issue about how many points you will need for this estimation to be good. Now, those of you who have statistics hats, which I don't, you can put them on and try in 25,000 dimensions, how many points you need to get stable estimates so that it actually makes sense when you use it. Some additional issues of size, and they apply both whether you have data or not. If you have 25,000 dependent random variables, you have over 310 million distinct correlations. And this problem isn't even big. Now, what do I mean when I say that? I'm not trying to be funny, right? If you want to do planning in a place like Beijing or a place like Paris, and you want to split the day in time and space, this is not big. If you really want to use it to do your distribution in Paris, this is a small problem. If we want to be practical as a war people, right? And I said there are methods to fix a matrix that is not positive semi-definite to become positive semi-definite, but with this kind of size, that's going to be an issue too. I mean, if you've done any numerics, try to invert the matrix with 310 million elements. And it's probably singular or almost singular. There are probably some zero eigenvalues in there. Something. But it's for numerical analysts, of course. And if you say, oh, but I'll take the really small one and put them to zero, so you don't have 310 million of them anymore, well, then you probably don't have a positive semi-definite matrix anymore either. Because you've ruined it, right? So this is not easy. So, but we need scenarios. We need discretizations for our models. So what do we do, right? And there's a nice paper with Chandro, Yabali, and Ray from 2016 that discuss many open issues in numerical routing. And one of the things they say about this type of problem, we probably likely need quite a large number of scenarios. And that's basically what I'm going to try to challenge. Because if they're right, it's not because I actually think they're wrong, but because if they're right, we're in trouble, right? So I hope they're wrong. Let me briefly say, what is a scenario in my context, just to come back to it. So it's a scenario, it has one outcome for each link in each period. So an outcome is a speed, right? So one speed for each, so it has 25,000 elements, okay? And I'm still two-stage, as I said, find a sequence of the customers, and then customer by customer, pick the shortest route. Of course, it would be nice to do it truly dynamic, like deciding which customer to visit next once you know how much stuff you have on board and what time it is. Okay, we're not at all there yet. Some more general words about scenario generation. Sampling is what you usually see in papers for people who do stochastics but are not interested in that. So they're interested in the logistics part, but they need to do the stochastics. Sampling is always possible, usually useless, because you get very low accuracy when you sample, unless you have a toy problem. But a good starting point is you need something to sample from, and I've tried to indicate now that even having something to sample from is going to be something of an issue. Right? Because if you don't have a proper correlation matrix, okay, only correlation is not enough, but that's assuming our normal then. So then we could sample, but right, you need a proper matrix before you can start thinking about sampling. Usually we sample and we don't think about it, but here it's an issue. And it's actually hard. Even if I give you a 25-dimensional normal, good luck in sampling from it when you start to come to the 23,247th conditional sample you need to make. So this is tough. You can probably sample from the empirical distribution, but of course then that empirical distribution better be a good representative, or you're going to do it with replacement and you're going to run into numerical issues again. But you could try, it's not wrong. And in the end, how many samples do we need in this phase? Well, I don't know, but I think I agree with Chandro and company there. We will need a lot. But I'll try to bring you onwards. So I'm very open. When I'm fluffy like that and I end in a ... it's because I don't know. And I don't think anybody knows, right? So there are lots of paths there you can investigate. But I have some thoughts, and that's what I'm trying to relate to you. And I would claim that apart from sampling, there is no method out there for scenario generation, for generating your discrete distributions to your optimization model, which is probably what is your favorite, that can handle this kind of dimensions. I think I'm right there. They couldn't handle it. They couldn't handle correlation matrices that they would have to handle just to generate the scenarios. 310 million, that's a nice number. Yeah. And of course, independent in this way is a little bit easier because the correlation matrix is so simple, right? So in some way, this is the one place where it's simpler. So what do we do? So if we cannot define the distribution, even a meaningful correlation matrix, for example, if we don't have data, or if we have data, we can, but we're not sure how good it is because we don't really have enough data, so all sorts of issues. What can we do? That's kind of what I want to ask you. Now, first I'm going to do something very technical. This is the more technical part of the talk, but I'm not going to do it. But this part is a little bit technical if you want to dig into it. So there's a paper by Couch from 2014. It's a purely technical paper about how to generate discrete distributions from something underlying. And basically what he takes as input are the marginal distributions, either as distributions or as discretizations. And he takes any subset of correlations. Now, he doesn't care which subset, because this is just a method, right? But he takes any subset of correlations, and what we use, we take the same link in neighboring periods and neighboring links in the same period. Those are the ones I showed you before. So we now define only those correlations, either from data or from guesses. They are not too hard to guess, because they make some sense. Of course, there are lots of loose ends yet, right? But that's what we do. And it fits with VRPs, right? Because what is a VRP? Well, it picks a sequence of links exactly, and 2 consecutive links in a route will always come from this set. You know, you continue on the same link in the next period, or you come to an intersection and you pick a link going out from that intersection in the same period. That doesn't prove we're right? But there is some logic to it. And because of the way the scenario generation method works, it always keeps means correct. So it means that the expected length of any route will automatically be correct. No, that's not enough, of course, but it will, because of how the method works. And in the largest case we look at, we specify 264,000 correlations. No, that's a big number, but it's not very big compared to 310 million, right? But, of course, right, there are some issues here. The method does not control the other correlations, so we will get scenarios that match the correlations we defined, but of course the ones we defined, well, they would be anything. In the scenario set, right, you can calculate the correlations in the discretization you end up using. And of course, for the ones I didn't specify, they could be anything. For the ones I specified, they will be what I specified, plus minus some small epsilons. Okay? So I have potential problems there, right? So what can that cause? Well, if the distribution route, so the distribution of on a route length, because that's a random variable, right, and that's where we pay the overtime, it will be off. If there are 2 links on that route, they will not be next to each other, because they are controlled. But there could be 2 links on a route that I didn't control, and they had a correlation that was wrong, and therefore the distribution of travel time on the route will be wrong. So that's something I have to worry about. And of course, these wrongnesses, any smart method would help. It probably helps to have a heuristic, because it doesn't quite go to optimality, but right? But when you have some correlations in there that are wrong, okay, they are not next to each other, but they are there, a smart method would try to put them on or not on the same route, depending on what that issue, what that is. If they were negative, if you end up with a big negative correlation, when you have a very good code, because that's what you're testing, right, it was, this negative correlation, wonderful, let's see if I can put them on the same route. That would be probably optimal, right? Now, what about when we solve it? So we assume that the problem is solved the way it usually is for big problems, also in deterministic. There is a part that finds a sequence of customers, and then there is a part that basically evaluates correctly in the stochastic setting the cost of that heuristic, that solution, right? And that means, and we're only looking at the second part, right? So in principle, if you have your favorite method for the deterministic version of the problem, and I can provide you with a way to value it in the stochastic setting, you can test your favorite method. Of course, provided that all I'm saying now in the end makes sense. I haven't told you that yet. But that's the idea, right? So in fact, the good old heuristic method for picking the route, which is a sequence of customers, you could try to use them, and whenever you have a sequence, I'll come in and try to give you what the cost is of that solution, provided I'm not killing myself with a number of scenarios I need to do it. So how do you evaluate a solution on one scenario? So now I have a number of scenarios. I still don't know how many, right? But I have a set of scenarios, which is this distribution of speeds. And now let's you give me a solution, which is a sequence of customers, right? What do I do? Well, first, if 2 customers are neighbors on a map, I've decided, I don't have to, but I've decided to travel directly. I'm just saying, if I have 2 customers sitting next to each other in two intersections in the city, the driver will not think about the long detour. No, I can calculate that too, no big deal. But then we go directly. It's just something we chose to do. And otherwise, we use the present speeds to find the shortest path to the next customer. So that's a Dijkstra computation. And I'm using discretization in time and space, but I'm using the speeds as they are when I leave the customer. So in other words, if you have a very smart system where the driver first thinks he's going to turn right in an intersection, and then suddenly computer tells him to turn left because his conditions have changed and he actually turns left, I'm not covering that. But once we value that travel, we use the real speeds on the scenario. Okay? We use the real speeds, meaning as it changes on the scenario, as time passes and it moves on links, we use the actual speeds on that scenario. So the travel time will not be the one we thought it would be when we did the Dijkstra. So how many scenarios do we need? And are they good enough when we find them? How many do we need? Likely many, Chandro and company said. And what are the issues? This is always the issues when you do scenarios in a discrete, in some discrete problem. If you have too few, you can solve the problem, but the result is just noise. Although it's optimal, right? It's optimal for the data you put in, but it's noise compared to the real problem. Or you have too many, and it's wonderful representation of the problem, but you can't solve it. And then we need to find this place in the middle, if there is a place in the middle. There are clearly problems which are so big that there is no place in the middle. But for some problems there are. And I think the one I'm showing you know, there is a place in the middle between just noise and can't solve it. And remember, we don't even have a proper distribution. We just have a subset of the correlations. I don't even have a distribution. What should I do? So let me see what we do. The one thing we have to test always when you solve a stochastic program is what I would call the stability. Okay, I need to speed up. So, but I want to do the stability test anyhow. So what do? Well, we take a few instances of our problem, right? They're all on the Beijing map. For each instance, we generate a set of feasible solutions. One comes from deterministic, but we generate a set of feasible solutions, typically the deterministic and some variants of that, assuming I can get a heuristic solution from that. Now, this one is, I think I need to be quick here. If you don't get it, you will have to ask me. Now, basically what we do here is that we generate, in this case, 9 scenario trees with our method. And we hope that when the 9 behave sampling, so think you were sampling. I'm not sampling, but assume you were sampling. I would sample a certain number of S scenarios 9 times. I'll come back to the 9 too, but I do it 9 times. And I hope when I solve the problem on those 9 scenarios, I basically get the same solution. Or in this case, I get the same value for those solutions that I have. If they're all over the place, S scenarios is not enough. Now, I'm not sampling, I'm constructing, and the method is deterministic, more or less, in its own right. So instead of having 9 trees of size 15, I have to make 9 trees from, well, where would that be from? 11, 12, 13, 14, and then they're different, and then it's like I'm sampling. I'm sorry if that was a bit vague, but I think I have to skip that now. But it's like sampling 9 trees, and then I'm going to evaluate my solution on all 9 and see if I get the same thing. If I do, I'm quite happy. If I don't, S scenarios was not enough. So it's like that, but it's a bit more awkward because the method is deterministic. So find the objective function for each solution and each scenario tree. And for each of them, I calculate the difference between the highest and the lowest objective function value I found. And if they're very far apart, then this is noisy and it's not good enough. That's the logic. And I pick the smallest S with acceptable relative difference. So what would it look like? Of course, usually tables are terrible, but I think it helps us there. So I have these, there it is. I have these solutions, so just let's look at just at the first one. This is one solution to the problem. It comes from deterministic model, so expected speeds. I have 10 scenarios, 30 scenarios, 50 scenarios, up to 1,000 scenarios, right? And I take the relative difference, so that's the biggest value I've seen minus the smallest value I've seen divided by the biggest. And they're all non-negative, so there's no issue of sign here. So if I have 10 scenarios, I get basically 5% is the biggest relative difference. And then it goes down at 50, 3.8, and at 100 is 1.6. Then the biggest number I've seen for 100 is, it's the 1.6. So if I take 100, of course this is a heuristic, right? If I take 100 scenarios, I will be below 2% all the time.
Right? This can be formalized, of course, but let's stop there. So if we do that, so again, I mean, if you see, for example, for 30, you see there are some bigger numbers there. There's a 2.85 is probably the biggest. Yeah, so that's the big. So I take the biggest number over all the solutions over all the trees of size 10, 30, 50, 100. This is called stability. And I start with a number of decisions. So what do we get? And this is where I'm surprised. And this is why this is interesting, otherwise it wouldn't be. So what is this? I put a ring on 15 here. So what is it? All is on the Beijing map, right? P equal to 60 is the case with 25,000 random variables. That's 60 time periods. This is the number of customers and the number of vehicles, so this is 9 routes. To get an error of 1% between the biggest and the smallest I've seen, I need 15 scenarios. Remember, I'm in dimension 25,000. Try to do numerical integration in dimension 25,000 and use 15 points. Doesn't sound right, right? This is something people have been wondering about for a long time, irrespective of my issue here. How is it that we can solve stochastic programs with so few scenarios and get good results when you look at what we teach in numerical analysis, if any of you teach numerical integration? What's going on? I don't know the answer. Wiser people than me have thought about that for a long time. Why can we solve stochastic programs in quite high dimensions with so few points? It doesn't seem to match what we teach in numerical analysis, where we integrate here we integrate an optimization problem. Something is going on there. Some of you are good at theory. That's something to figure out. So what's going on? Well, in 25,000 dimension, we need 15 scenarios to obtain relative difference for the biggest problems. The larger the problem instance, the map is always the same, but larger means more and more time periods and more vehicles. The fewer scenarios we need, which sounds kind of backwards, right? You would think the problem got bigger, you need more, but you need less. And the errors caused by the strange correlations are hidden inside here. I know I was a bit quick with the stability. So if you want to dig in, you will have to do that. But the errors caused by potentially funny correlations, and there were funny correlations in there, because I only control some of the input correlations, they are hidden in the 1%. We need, but this is one step. We need fewer scenarios for larger cases because the errors from incorrect correlations, they kind of get averaged out because there are more routes. So there are some incorrect correlations, but because they sit inside more and more routes, and the number of periods or the number of kind of road links in each route becomes bigger and bigger, and each error gets smoothed out. But there is one thing worth seeing, and that's the error never goes to 0. But I'm happy with 1%. But if you want 0.001%, this doesn't work. So I'm happy with that, but it never goes to 0, because I will always have funny correlations in there. But I think 1% is fine. If you have data for more than 1%, you're clever. We said I used 9 trees. I have to weigh my arms a bit here. We said 9 was a bit randomly chosen. Here I've gone up to m equals to 10, so that's 21 trees, and I'm still below 2%. So this is quite stable. No, this relative difference is bound to increase when I increase the number of scenario trees, right? Because I do the max. So it's bound. But even with 21 scenario trees, I still have a fairly small number. So I'm happy with it. Of course, I'm a heuristic person in my mind. So I think that's okay. We also did a proper in-sample test. In fact, we took all these scenario trees and we solved them, but of course with a heuristic from the literature, not from optimality, and we still get basically the same numbers. So this is a proper in-sample test. It means for every scenario tree, you solve the optimality, well, when that code stops, right? And then you compare the biggest and the smallest. So I didn't have a fixed set of solutions now. I solved for every tree. And this is more a classical in-sample test, and the numbers are basically the same. And then we did a proper out-of-sample test, but it means you basically take the solutions from one tree and stick it into all the others. You can't sample here because you have nothing to sample from. So you cannot do a full-scale out-of-sample test because that needs something to sample from, and you don't have that. but you take each of the solutions, and you stick it into all the other trees, and you see how stable it is, and it's very stable again. Again, you can read about in this paper of 2007, which is a very simple paper, but it sort of discusses the issue of stability. CPU comments. For the case where p equals 30, this was the second largest, so this is 12,500 random variables. It took us 37 minutes on a normal laptop to calculate the scenarios. But remember, this is offline. And this doesn't change as long as the map doesn't change, or the traffic condition change in a systematic way. So this is an offline calculation. But after all, they have 180,000 elements, and they handle about 130,000 correlations, so it's not that small. For p equals 60, I could report the elapsed time, and it's mostly swapping, because it's bigger than our memory. So you need a bigger computer to go beyond this. It's not algorithmically stopping, it's stopping on size. So you need to create these scenarios, but it's offline. And remember now what we're doing. 15 means that when you run your heuristic of finding a solution and evaluating the solution, each iteration will take 15 times more CPU than the deterministic case. Now, 15 is a tough number, but I had expected in thousands, to be honest, for 25,000 dimension. But it's 15. So you can actually try your favorite VRP here in this setting, and it would run per iteration about 15 times slower. I put it that way because I have no idea how many, it depends on your method, how many more, it could be more or less iterations, right? But each iteration will take 15 times more time, because you have to evaluate the solution on 15 scenarios instead of 1, which is the deterministic case. And you can still do your heuristic in a node network, in a customer node network, if you want to. We have tested this also on other VRPs with time windows, hard and soft, fuel consumption instead of distance, fixed cost for vehicles. So we have tested it on all sorts of other VRPs, and we still get around 15. I mean, sometimes we get 20, sometimes we get 10, but we don't get suddenly 250. So the numbers seem quite stable. We have done it on stochastic shortest path problems with real data, but only shortest path, so it's a bit weaker. I want to report on that now. And for the moment, we are doing what I have talked about today, but with the real speed data from Chengdu. That's what we're doing now. But I don't have the result. So I think we have a method, or at least an approach. Maybe method is a bit strong. I think we have an approach that we can evaluate the objective function for correlated speeds in very high dimensions, and I call 1% very high accuracy, because I don't think any of your data are beyond 1% anyhow. I mean, I think this 10 to the minus 8 is a joke, because we never have data for it. Major issues: an argument that these problems cannot be formulated on a customer node network. We need stability testing to find out how many scenarios we read. Very often I see papers where people solve, and then we sample 25 scenarios, and maybe what they solve is only noise, but nobody worries, because they don't implement it, of course. Nobody uses it. Stability is important and very much undervalued. And we have a scenario generation method very well suited to VRPs, because the correlations we picked are exactly following the paths of a route. So it's not accidental. And I think the number of scenarios is very modest. And kind of contradicting what Jean Dro and company said. So this is coming to the end. So why I would call this, did this work? As I said, if you care a lot about accuracy, maybe you don't. But I say it worked. And why did it work? Because we know which correlations are most important, because we know the shape of a solution. And I think there's hope in other models, and I'll just give a few examples. Demand, if stochastic demand, well, you care about the customer that is close to each other, because they are the ones that are likely to end up on the same route. So I think there's hope down there. Facility location, demand and speed. Speed will be just as here. And when it comes to correlations of demand, same again. You don't care about the north and the south end of a 10 million city, right? You care about customers that are close to each other. So then there's hope. An example where it wouldn't work is portfolio management from finance. No chance, because you have no idea which correlations to pick. So you have 310 million of them, if this was a dimension of the problem, right? And you're going to pick a small number, and you have no idea which ones. Then I don't think it would work. So I think this issue is kind of wide open. Now, I know I'm ending, but I'm asking you the one last question, which I don't have a slide on purpose. Okay, you observed I said 15, and maybe some of you were surprised how low it is. But how can it be that it is so low? I think I have an answer now, but it took me a long time to think I have an answer. It's extremely low in dimension 25,000. And I send by the last sentence there, not portfolio management, it's not general, right? Now what, at least if you work with scenarios, and I have said the following. I have a route of a car, and it visits 8 customers, and it travels on approximately 25 links, which means I have 25 random variables. How many scenarios do you think I need to accurately calculate the travel time of that route? Maybe you have no idea, but 15 wouldn't sound totally crazy. So what is the clue of that method of count? And why does it use so much time? Because it is doing it route by route when you use it. It's basically fixing these scenarios so that for every meaningful subset of these short routes, it produces a good solution. So 15 is not an unreasonable number if you had 25 random variables on a route. I mean, I have some experience with this. So this is low, but no, I wouldn't jump if I saw it. So I think the clue is that it's a union of all routes, and all routes are fairly short, after all, right? You're not visiting 200 customers on a day. And the method then, which is why it's so slow, as the scenario generation method, is that it needs to get this right for all the subsets. And it wouldn't happen in the portfolio management because there's no natural subset, and then 15 is ridiculously low and wouldn't work. Yeah, that's it. Not too bad.